15.8, number 1, part A. You start out with a system of equations. U is x minus y, v is equal to 2x plus y. You meant to reverse this to get x is equal to some expression involving u and v, and y is equal to some expression involving u and v. And you have done this before. It's prerequisite material. I have a way that I like to teach people to keep track of all the information here, and that is to group together these equations. It is a system of equations, and change it into another system of equations. What I'm going to do is see that if I add u and v, thereby adding their right sides as well, all of the y's go away, negative y plus y. So I am left with just, oops, shouldn't have written that plus sign, x plus 2x on the other side, which is 3x. Okay, so u plus v is equal to 3x is what I get by adding these two equations. And I can rewrite one of the equations. I could write v is equal to 2x plus y again if I want to. V is equal to 2x plus y again. And then group the resulting system of equations and simplify again. Or I can think to myself, hey, you know, instead of doing that, instead of wasting that energy, what I'm going to do is think about the fact that I could just say that this means that x is 1/3 u plus 1/3 v. Notice that I put u and v, these two terms, in the order u then v, the order that the variables are meant to come in, right? X then y, u then v. Variables are ordered. Now, what I'm going to do is I'm going to use this and substitute it into that first equation. That amounts to substituting this into that. Which, you know, I could write out the slow way. Like I said before, I could rewrite this and then substitute that into that and put it over here. But what I'm going to do is just a somewhat faster way to write this. I call this advanced elimination. I'm showing you advanced elimination because I assume that you've done pretty simple elimination before. Okay, if I'm going to replace x with 1/3 u plus v, then I can rewrite this equation as v is equal to 2 u plus v divided by 3, right? U plus v divided by 3, and then I still have my plus y. And that will allow me to get y by itself. Okay, if I isolate y, how many u's will I have? Negative 2/3 u's. Moving them to the other side. And how many v's will I have on the other side? Well, I already have 1 v, and I'm going to take away 2/3, and that will leave me with a total of 1/3 v. So I can write v over 3 or 1/3. Okay. So, based on that, I'll say that the Jacobian partial of the coordinates x, y with respect to the coordinates u, v. That's meant to be the absolute value of the determinant of the matrix of functions dx, du, dx, dv, dy, du, dy, dv. Right? First coordinate, x, for the first row, second coordinate for the second row, u for the first column, v for the second column. All right, let's just write out what those four entries are, dx, du. Here's x. X depends on u this way. The partial derivative of x with respect to u is 1/3. And the partial derivative of x with respect to v is also 1/3. The partial derivative of y with respect to u is negative 2/3, while the partial derivative of y with respect to v is 1/3. That is equal to the absolute value of 1/3 times 1/3 minus 1/3 times negative 2/3, and that absolute value is 1/9 plus 2/9. That's 3/9 for a total of 1/3. The absolute value sign just goes away. Okay, so the absolute value of the determinant of the Jacobian of this coordinate transformation is 1/3. And we'll be able to see what that means in part B. And I'm back. Well, I meant to figure out how this coordinate transformation changes the triangle defined by these points into some other shape. So let me go ahead and give the sides of this triangle some color. I'm going to give this side blue as a color, this side green, and the other side is going to be red. And I'm going to track those colors going from the XY plane to the UV plane. One thing that can be nice to do before we begin is take a look at where the individual points go, and then we'll take a look at where the lines go. 0, 0. If x and y are both 0, then u is 0 minus 0. Okay, so that's 0. U is 0. And v is 2 times 0 plus 0. That's also 0, 0. So this point gets taken to that point. All right. How about 1, 1? U then would be 1 minus 1, so u is 0. I'm going to be somewhere along this line. And v is 2 times 1 plus 1. That's at 1, 2, 3. Okay, so the point 1, 1 is taken to the point 0, 3. Again, put in 1 and 1 for x and y. Get 0 there and 3 there for u and v. Okay, last point, 1, negative 2. 1, negative 2. So 1 minus negative 2, that is a positive 3. So let me make some tick marks here. 2, 3. I'm going to be a positive 3 somewhere along here. What is v going to be? 2 times 1 plus negative 2. That's 0. That'll put me here. So this point goes to that point. The point 3, 0. Okay, so it would be a little bit naive of me to just follow these lines and say, since that point went to that point, this point's going to that point. Let me try to be just a little bit more sophisticated. I'm going to take this blue line, and it is, of course, the solution set, well, it's part of the solution set to y is equal to x, right? Y is equal to mx plus b, slope of 1, y-intercept of 0. And that is equivalent to y and x in terms of u and v look like this. Okay, so y is equal to x as an equation involving u and v is negative 2/3 u plus 1/3 v, that's y, is equal to, and x on the other side, x is 1/3 u plus v, just trying to simplify things, I'll write 1/3 u plus v like that. And let's clean that up a bit. I see that I can cancel the 3's all across here. I've got negative 2 u's, and if I bring all the u's to one side, we'll have just 3 u's, 3u. And how about the v's? Oh, there's 1 v there and 1 v there. That cancels, so 3u is equal to 0. Okay, of course, that just means that u is equal to 0. Okay, so the blue line there is the line u is equal to 0, and goes from that point to that point, which was this point to that point, just like this. So that line became this line. See, each point in blue, like that point right there, is going to go to somewhere in the middle of this blue line, according to these pair of functions over here. Okay. Well, what should we deal with next? How about the green guy? In green, that is part of the solution set to the algebraic equation x is equal to 1. Now, in terms of u and v, that is 1/3 u plus v is equal to 1, or u plus v is equal to 3. So u plus v is equal to 3 has slope -1, y-intercept 3, so that line. And in going from there to there, we go from there to there. Every point on this green line, like that point, is going to go to some point on that green line according to these maps. And last, in red, I'm pretty sure I know what's going to happen. You need to close up this triangle, so we're going to get that line right there, but let's just make sure. That line is y equals mx plus b with a slope of -2 over 1, rise over 1, -2 over 1, so -2x, y-intercept of 0. And what does that look like in terms of u's and v's? Y is -2/3 u plus 1/3 v, and x is 1/3 u plus v. I see that I can cancel the 3's, and -2u and -2, looks like the u's are going to completely vanish. We'll have a v there and a v there, and -2v there. So let's see, we get 3v is equal to 0, or v is equal to 0. And v is equal to 0 is that line. Okay. So these 3 lines go to those 3 lines. Every point in the middle of this red line, like that one, will go to some point in the middle of that red line. And I just want to quickly look at something with you. The volume of this thing is 1/2 base times height. 1/2, since it's a triangle, its width certainly is 1, right, from there to there, and its height is from -2 up to 1, 3. Okay, so that is 3/2. Well, the volume over here is going to be different, and it's going to be different by that factor. The volume of this, stupid of me to use V for volume. Volume. The volume over here is 1/2 3 height times 3, which is 3 times 3/2. So what factor is in between 3 times 3/2 and 3/2? It is this factor, 1/3. The absolute value of the determinant of the Jacobian is the factor by which volumes of shapes change. Now, this ended up being constant, 1/3. The absolute value of the determinant of Jacobian is not always going to be a number. It will sometimes be a function, as you should see in lecture, in going from, say, xy coordinates to cylindrical coordinates or to spherical coordinates. There, the absolute value of the determinant of the Jacobian factor, that is going to be a function that depends on where you are in R and where you are over here and where you are over there. Could you imagine some parts of this picture stretching more than others to go from here to there? In a sense, it looks like this picture just sort of rotated and the lengths of these various sides shrunk or expanded. This kind of thing, where you simply rotate and shrink and expand, that's a linear transformation. You'll be studying that a lot in linear algebra. Jacobians go beyond that kind of transformation, and they go to cases where the coordinate transformation is not linear. You'll probably study that quite a bit later on if you get to differential geometry.